All right, everyone, we're going to get started with our next session. We will continue to focus on applications of soil moisture data in research, but with this session, there's going to be a much heavier emphasis on satellite data. So we'll be looking at the L-band quite a bit. Your agenda says the moderator is Trent Ford. I am not Trent Ford. So if there's any stupid questions from the moderator this session, you will know why. My name is Peter, and our first speaker comes to us from the University of Georgia, and this is Matt Levi.
All right. Good morning, everyone. Thank you for the introduction. I'm going to share with you some of the work we've been doing collaboratively at UGA with some of folks at Tyson Auctioneers Group in Oklahoma State, also partners with USGS. And a lot of this got started because we were really interested in trying to predict wildfire, as you've already heard a little bit about. And so we're trying to find a simple approach to get us some soil moisture data in between the measured values. And really, this photo is an example of the landscape we're working in the Red River Valley. And that's what most of the data will be. I'll show you today. This is the Red River and the North Fork of the Red River confluence. So you can see quite a diverse landscape. We're trying to figure out what's happening in between all those measured points among the cropland and rangeland. I don't have to tell you that soil moisture is important. That's already been well established. You already know this. And, this is sort of my required introduction slide, but just kind of point out a couple of the other applications that we were thinking about when we're trying to think about prediction of soil moisture across these watershed scales. And so obviously we're interested in drought, irrigation decisions, and other management activities. Of course, wildfire was a big driver in what we're trying to do. And then another one that we haven't talked about yet, but the applications for soil taxonomy and how dynamic soil survey is sort of becoming more of an interest, and thinking about the soil climate in particular. We obviously know that, understanding the modeling between the point measurements is the challenge here. And so we instrument sites very heavily. And then we can get products, though, at large spatial scales. And this is part of what I'm going to present today, is thinking about something like the drought monitor. You can see a snippet here showing a region of interest. And so how do we connect these point measurements to the regional scale? And how do we evaluate that? So what are some of the options in terms of available data? Obviously, we have a lot of networks. Some of them are a little bit spread apart. Some of them are really densely oriented and available. Of course, we can fill in the gaps with some remote sensing products like SMAP and SMOS and others. Of course, they have a focus on the surface. Even with the application of land surface models, we can go deeper in the profile. And one of the limitations I see with those data sets would be that there's a limited period of record. And so if we want to go back further to look at something like a long-term record of wildfire ignitions, then we might need a different product. Some of you may be familiar with the Soil Merge product, which is developed as part of a Texas A&M and USDA ARS effort. This has a very large spatial footprint at 0.125 degree grids. However, it does go back in time and it looks at the soil profile in full, but there's a limitation in terms of the spatial resolution there. And of course, we've already seen some examples of land surface models. Obviously, they're very data hungry and they need a lot of information to really figure out what's going on. So again, our objectives were to develop a relatively simple soil moisture prediction model that would give us an adequate spatial resolution, temporal resolution. In this case, we wanted a daily product. And also we want to look at the depth within the soil profile, get beyond the surface and go down into the root zone and even deeper to a meter. So what we tried to do is reharness something that NRCS was already using for soil taxonomy, the Newhall simulation model, which is a simple water budget approach. It is a monthly time step, and we wanted something that was a daily time step. So we had to modify this. We're doing this in R, and we're making an R package called R Newhall. And really we want to figure out what's happening within the profile, but think about scaling this up to a little bit more reasonable pixel size. So the Newhall simulation model is a monthly water budget approach as is designed to look at soil climate. And so the interest here is thinking about when water is incoming to the soil bucket or the soil sponge, as I like to call it. When do you have a surplus? And so when are you having utilization of that soil moisture? And then when do you have a deficit? So that's kind of the idea that's built into the soil taxonomic interpretation. So we've been working to replicate that approach, but using R for this. Some of the work by Newhall and others originated in the 70s and 80s. And so for some reason, there's an 8x8 grid of the soil profile that was used as the mechanism for water in, water out. And so if you have 64 squares and you divide 1/64 of that soil sponge, then it becomes a little bit complicated to interpret and understand, okay, how much water really is that? So this also includes cost layers to move water from one of those rows to a lower row, and then also by the same method, removing water from the surface through ET. So we basically have revamped this to make it something a little bit more interpretable using a 10x10 grid. So now we have we have 100 possible grids and grid cells. And so we've updated this to try to think about, again, a daily time step, incorporating data from Surgo that would relate to the water movement within the profile. Obviously, texture is important for water holding capacity, and then measurements of water content at field capacity and wilting point, right? So we can represent now the wilting point here on the dry end, field capacity, and then we actually added a saturated column because we recognize a lot of times our soils are actually saturated and beyond the third bar. The metallurgical data that we've incorporated here is relying on MOISST for ET, and then as well, we're using some data inputs from PRISM for climate, temperature, and precip. So the study area is about 93,000 square miles. It sits, Red River actually is part of the border between Texas and Oklahoma. And so it's a very large boundary. We heard earlier about the gradient of precipitation from the panhandle of Oklahoma all the way to southeastern part of the state. There's a huge gradient of 15 inches to 60 or 70 inches or so in the southeastern part. And so this would classify as an ustic aeritic to aqueic moisture regime from a soil taxonomy perspective, for those of you that are inclined to think of things that way. We started working at the Marena site. You heard about the Marena testbed site. We used one of those areas, some of those points within the Oklahoma mesonet to start training the model and at the point scale at different depths. And so in many cases, we got very good agreement between our measured and modeled soil moisture on a volumetric water content basis. You can see field capacity and wilting point plotted here. I wish they all looked this good. As probably not surprised, there are areas where we have some errors, right? So we're trying to figure out how we can tweak the model enough that we're not getting way too complicated, because we want these inputs available so that we can then apply this at a larger spatial scale without, supercomputing. So I'm just going to jump to some results here to give you an example of some comparisons to SMAP products. So basically what we have here is a daily correlation for the year 2000 or for 2016. We looked at the daily values from SMAP and compared that to our daily values from our Newhall simulation approach in the root zone. And you can see that these are Pearson correlations between those 365 days. Okay, so what jumps out to you is probably jumped out to me is that we have this sort of gradient of which corresponds to about a 500 or 600 millimeter of precipitation zone where the relationship sort of breaks off, right? So this is the dry end of the state, the dry end of the study area, and our correlations are weaker on that end of the gradient. So if we look at individual stations across part of that study area, 34 stations in the mesonet, take the difference between the measured and predicted volumetric water content at two different depths, 5 centimeters and 25, you can see that we have, basically we're over predicting with the model. One thing I didn't mention is that an assumption of the Newhall model is that we have a freely drained soil. Okay, so we know that on the landscape, we often have root limiting layers, we have water that's not freely draining, and we have different scenarios of soil depth and so forth that we're not really explicitly accounting for in our model right now. So this kind of begs the question of, back to that original slide, when we have a point measurement, how should we validate that point measurement to an 800 meter pixel or a 4 kilometer pixel? How closely representative of that pixel is the soil that we have a measurement in, right? So I kind of bring up the question here, do we really need to be validating all these products using volumetric water content? Obviously, it's the gold standard. If we can do that, then we're doing an awesome job. But can we use soil moisture condition instead? That's been touched on a little bit already yesterday and today, to think about wet, dry, moist conditions, right? And so thanks to Tyson, you've already got an introduction to the fraction available water. I have the equation here again. So we've got volumetric water content that's measured minus the wilting point, and then that's divided by the fraction, the field capacity and wilting point, right? That's our size of our sponge. And so if we convert a volumetric water content, this is 1 point over the course of a year from January to December, we can convert that to a fraction available water. Okay, and then we can impose a threshold of what is dry, what is moist. And we can start to think about comparison of our models from a point scale to a spatial footprint that's much larger than that point. So we can also get other interesting statistics from this kind of approach to think about classification from a soil taxonomy perspective, to think about how many days are moist and how many days are dry. Okay, if you ever read soil moisture regime definitions, you know that it's so many days consecutive moist or dry, and then cumulative days moist or dry. Those are some of the criteria we need. So we could start to look at the statistics and distribution of these data. For example, you can have number of consecutive days moist over the course of 1 year, or you could incorporate multiple years. And from here, we can get things like soil moisture regime criteria, but we can also think about how the patterns of soil moisture are normally changing at a particular site. And instead of using volumetric water content as obviously the gold standard, but think about how to do this in other ways. So if we think about one particular day and we put a threshold into the same watershed, we've got dry conditions for a 0.15 fraction available water versus a 0.25. You can see that the patterns change on the landscape. And so the big question is, what's the right threshold? That's something we can talk about later. And maybe if you have insight, I would be happy to hear what you have to say. You could also think about the cumulative number of days moist in a particular year. And so again, the patterns of the landscape start to really jump out at you. And the threshold is going to be the key here to figure out what's moist and what's dry. Obviously, we can see the maximum consecutive days moist. This is another statistic that we could derive using this approach. And so we can see that the moisture conditions are very sensitive to that threshold that you choose. And so trying to find the appropriate threshold is really the key. But I think we have the building blocks to improve our interpretations of soil moisture for more applications. We are working to develop this R package. One of our collaborators and co-authors here, Dylan Bodette, is helping us from the R side of things in terms of development of a package for our Newhall. We're almost done with this classic version, which many of you may have used before. And so we're then trying to enhance this to make it a little bit more appropriate for a daily time step through the whole profile. One thing, or a couple of things we haven't really accounted for are the spatial redistribution of water on the landscape. You can see this Saga wetness index here. This is from Southeast Arizona, a place where I've done a lot of research as well. And you can see that we know water is being redistributed on the surface and near subsurface. And that's something that we have not yet incorporated to this approach. And then looking at soil moisture measurements, we know that it's not always a linear trend. We often have, interesting distributions of moisture with depth And so these are some of the challenges that we're facing. Just want to acknowledge the funding sources, USDA, NRCS, cooperative agreement helps support this, as well as the South Central Climate Adaptation Science Center grant. So I don't know if I have any questions, but thank you for your attention.
Yeah, questions for Matt?
Thanks. How did you identify the retention endpoints for your fraction of available water, the water content at permanent wilting point and field capacity?
So those were based, so essentially those were based on the Surgo data for field capacity and melting point, which would in theory be related to measured values. Of course, at the spatial footprint of the input data, you know, from Surgo, that's aggregated up to be equivalent to the PRISM 4 kilometer or 800 meter data. A lot of that gets kind of mixed up, but it's based on Surgo as an input.
Then Matt, I had a quick question for you. Is topography accounted for at all in some of the finer scale estimates of water availability in the Newhall model, or is it not dealing with that?
I don't think it deals with that. It's really just like, it's a water budget approach, like a bucket model. So it's water in from the top and water out through the bottom. We recognize that, you know, we need to figure out how the redistribution of water would be added. And so I think we're trying to honestly try to stay away from some of the hydrologic models and getting too complicated with land surface approaches, but we'll incorporate enough to try to keep the model running without getting too data hungry.
I'll ask the online question. Are the MOISST ET used in the model were validated with some eddy flux towers around the sites, if any? What method was used to calculate ET?
Yes, so the MOISST data were not checked against eddy covariance towers. They were taken as the actual ET value. And then we actually looked at a ratio of actual versus predicted using the Penman Monteith as a ratio to account for that water out.
And our last question for Ben.
Yeah, that kind of gets it. That online question is sort of similar to mine about the ET calculations. But I mean, this is, my gosh, well, you and I have a common friend that we are working on something similar with. And so, you know, I don't know if you look at James Dyer's work with the climatic water deficit, but that does, I think, include a topographic element to it using a digital elevation model, and then, you know, using slope and aspect and hill slope position to kind of account for solar radiation loads and things like that. And also, I think it uses like you know, the top model as a way to route water through the system, which is not perfect, but you know, it's something. So those are all things to maybe consider as well. I don't know if we've considered those or seen James' model at all.
I've not come across that work, but I think I'll find you after we have a break. Thank you.
Thanks again, Matt.